Okay, let's come back. Let's hit a couple new things and talk about skeletal muscle contraction. Let's put all these moving pieces together, all these terms you've learned about today. So let's look at that complex troponin was making because we need that to all work together for this contraction to happen. So remember, troponin had three little parts to it. It was going to bind to actin on one side, and it was going to bind to tropomyosin on the other side. And when it did that, then what happened was the myosin head could not get into the binding site on the actin molecule because tropomyosin was acting like a chastity belt. But if calcium would come along and hit onto the troponin, it would cause the troponin to move, shift, and it would pull the tropomyosin off the binding sites of the actin, thereby exposing them, as you can see in this second drawing. And then what that allows is the myosin heads to go into those binding sites. So when calcium ions come along and they bind to the troponin, that forms this complex between actin, tropomyosin, and calcium that pulls tropomyosin aside, exposing the binding site. And when myosin enters the binding site, then we form a cross bridge between actin and myosin. So another term here, a cross bridge is formed. And so this shows the cartoon drawing, which I shrunk down and overlaid over an electron microscope picture showing the myosin with the myosin heads going into the actin binding sites, forming a cross bridge. So how does this happen? Well, it happens because it's exposed, and now because we have formed this cross bridge, we are going to be able to have contraction because the myosin head brings its own energy source. So myosin already has ATP bound to it. So here's what that looks like, okay? That myosin head is what we already call cocked and ready for action. What has happened was an ATP molecule bound to it and broke that ATP bond down. So now there is an ADP and an inorganic phosphate, as well as the potential energy being stored in that head of the myosin molecule. And so once the calcium molecule comes along and exposes the binding site on the actin, and the myosin head can form a cross bridge, the myosin is going to lose the inorganic phosphate. The ADP is going to be there. The potential energy is there. And now the potential energy is going to become kinetic energy. And that cocked myosin head is now going to form what's called a power stroke. So instead of being potential energy, it's going to do kinetic energy. And it's going to be pulling on the actin that is inside of it. It's going to be using that energy. So the ADP is going to fall off. So now the myosin is still caught inside the actin. It has used up its energy and it's kind of frozen in that position until a new ATP can bind to it. And when the new ATP binds to it, and is broken down to ADP and an inorganic phosphate, that actually causes the conformational change, which allows that head to detach from the myosin. Okay, because otherwise, without the ATP, the myosin is going to stay attached to the actin. All right, so let's put this all to work. So each cycle is going to use the energy from one ATP molecule, and this cycle is going to be this huge theory that we call the sliding filament model. So here's how it works. The myosin heads are going to be binding to exposed active sites on the actin. Okay, so we've already had the calcium come along and pull the tropomyosin off. So we have exposed active binding sites. And so now the myosin head that's already been pre-primed with the ADP, already has the potential energy in it, is going to bind and form a to that exposed site. It's going to happen on both ends. So not only on this end, but also on the other end. And remember, it's a whole 360. So it's also going to happen on the actin here, as well as the actin there, as well as actin front and back. A whole 360s worth of actin is going to happen. And now it's going to use that potential energy to pivot inward and pull the actin towards the center of the sarcomere. So that myosin head is going to have its power stroke. And the power stroke is going to cause those actin filaments to slide towards the center of the sarcomere. In other words, we're going to have sliding filaments. So the myosin heads are moving, but the myosin itself isn't moving. The actin is what is moving to overlap the myosin more. And then a new ATP binds to the myosin head to detach it. So here's a little GIF. And I know you're all enthralled by the myosin head, but let's not look at the myosin head yet. Let's look in the upper right-hand corner where you see the little brown ball flying in. And when you see the little brown ball flying in, you will see it attaching to the little purple balls, which are the tropomyosin. So the little brown ball flying in is a calcium molecule, which is attaching to troponin to form that complex, which is the three purple things, which is then attached to that blue linear structure, which is the tropomyosin. And you can see when the calcium comes in, that is pulling the tropomyosin to a different position on the actin. And then that allows the myosin head to bind and pull, bind and pull, bind and pull. And then the myosin head is stuck there. And then you see a new ATP flying in from the bottom right. And then you can see the ATP detaching. Okay, so as long as we've got calcium flying in and ATP flying in, we're going to keep on doing this. So go back, review it all you need. Here we have 2 electron microscope pictures, 2 cartoon drawing pictures, and then I've added 2 stick figure pictures. The top picture of each is showing before contraction. The bottom picture of each is showing after contraction. Okay, so before, after, after. And then here are the questions that you need to be able to answer. After contraction, what has happened to the length of the actin filament and what has happened to the length of the myosin filament? Answer those 2 questions first, and then answer what happened to the length of the A band, what happened to the length of the I band, what happened to the Z lines, and what happened to the sarcomere. And I'll give you a word bank, and the word bank these are the only choices for your answers. Did it shorten? Did it lengthen? Did it stay the same? Did it get closer? Did it get further apart? Please do not Google, do not look up, do not use any other answers. You don't know the answers at first, go back, rewatch supplemental videos, do other stuff. Don't ask other people the answers. Don't go to the tutor to ask them the answers. Go to the tutor to have the process explained to you. Make sure you understand it. Can you teach it to somebody else? Then try to answer the questions yourself. Ask the tutor if your answers are correct. And if not, don't ask the tutor the correct answers. Try to work it out yourself. Change your words from, I know, good enough. It's okay. I didn't get it all, but I got enough. 2, is this really my best work? Okay, with this, we're done with the first day's material for skeletal muscle, and I will see you when we come back to attack the second day, which is a lot easier than the first day. So I want to thank you so much for your hard work. Really put in the work today for all the videos today, realizing that the second day is going to be easier. Thank you so much, and I will see you next time.